or close. All right, there we go. So I'm gonna go ahead and up my volume here. There we go. All right, we have a couple minutes before we begin, but please pay attention to the weather tomorrow. I've heard rumors that classes might be canceled tomorrow. It's too icy and it's too unsafe for you to travel. So be careful. Look for your emails. I'm sure everybody does isn't partial online anyway, so it will be fine. But be careful. Be safe. I know I have lived in the South all my life. I got stuck on the mountain. Snowy, icy weather, and I had to have some guys from Michigan help me out. So if you know some guys from Michigan to help you out, definitely try to travel if you can. But the rest of us who love to travel in Texas because it's not icy or snowy, stay home, be safe. Okay, that puts us almost on time here. We got just one more minute before we begin. And so we have about 13 people online. Has everybody been able to go and access the YouTube site with the lectures? Okay, notice there's a 11 a.m. lecture, but there's also a 2 p.m. lecture. One's usually better than the other. So if you went to one, go to the other, and then maybe you can, maybe glean some new information there. So we're on about the same pace, okay? We were supposed to have a quiz today. Of course, that didn't happen. We're going to have that quiz on Monday. Sorry, I want to try to get us back on our thing. It'll be up to chapter 2, excluding IR. I want to have a separate quiz just for IR, which will be on Wednesday of next week. So Monday, we have chapters 1 and 2 predominantly without IR on Monday, and then IR only on Wednesday. Okay. So write that down. That's going to be Monday, and then that'll catch us back up to where we're supposed to be. Okay, so we'll be on track with where we are in class, where we are in lab, where we are in our quizzes, and we'll be set to have our exam on its currently scheduled day. Okay, so that being said, let's go ahead and continue on where we were. Before, we were talking about the different types of carbons, and we had the type of carbon was based on how many other carbons are bonded to it. So we have primary with one other, secondary, quaternary, etc. And we found out that we also had those hydrogens on those carbons carried that similar name. Okay. So if the hydrogens are on a primary carbon, they are primary hydrogens. Okay. So this designation of what type of carbon and what type of hydrogen is very important. But that also extends to other functional groups, okay? So when we go to things that were like alkyl halides, basically we have a halogen instead of that hydrogen, we carry that same designation that we had with those hydrogens. So let me, grab a stylus here, mute my watch. Okay, so if we have let's just say, let's give this compound here, and then we're going to add to it the chlorine here, the fluorine here, and an iodine there. Okay, so just like we did with the carbons and hydrogens right here, we're going to designate those halogens by the type of carbon they're attached to. So that makes this first group here, this fluorine, what kind of designation does that have? Primary, secondary, or tertiary? It's going to be a primary alkyl halide because this is a primary carbon. It only has one other carbon attached to it. So that's going to give it the primary designation. When we start talking about reactivity of alkyl halides, primary alkyl halides tend to be more reactive because there's less groups in the way. So knowing that it's a primary, secondary, or tertiary is going to become important. So let's look at this chlorine right here. What kind is this? Primary, secondary, or tertiary? Secondary, because there are 2 carbons attached to this carbon here, which makes this last one tertiary. Okay, there's 3 carbons attached to that carbon that has the halogen on. So we look for the exact same thing in primary, secondary, tertiary carbons, and the same nomenclature we use for those hydrogens on those carbons as well. Now, what if you have an alcohol instead? So let's do OH and OH and OH. We're going to look for that exact same structure, right? We're going to say that, oh, this is on a secondary carbon, which makes this a secondary alcohol. This is on a tertiary carbon, so it's a tertiary alcohol. And this is on a primary carbon, making it a primary alcohol. Okay. What we're going to see is that as we look at that primary, secondary, tertiary, they have different reactivities. And they're going to have different reactivities for different reasons. But knowing that designation is very important. Now, that works for hydrogens, that works for halogens, and that works for alcohol. Okay. But the amines are different. The amines are how many carbons are attached to the nitrogen. So this is backwards. This is the one that's backwards. The amines and the amides are backwards. And that case here we have, in the case of here, this is technically an inorganic compound. Why? There's no carbon. There's no carbon-hydrogen bond. So ammonia is an inorganic compound. But if we take that and add a carbon chain to it, okay, is that a primary, secondary, or tertiary amine? It's a primary amine, not because the group, the carbon it's attached to is primary. It's primary because there's only one carbon attached. One carbon, primary. Now, if we take that and have this over here, and of course we have those lone pairs, don't forget those. What kind of amine do we have now? This is a primary carbon, this is a secondary carbon, this is a tertiary carbon, but what kind of amine do we have? Tertiary, because it has 3 carbons bonded to it. Okay, amines are backwards. How many carbons are bonded to the nitrogen tells you whether it's primary, secondary, or tertiary. Okay, now that, of course, I can just draw the secondary one right here. And that's a secondary amine because it has 1 hydrogen and 2 carbons bonded to it. And don't forget that lone pair. When we're starting out, always write your lone pairs because it tells you molecular shape. Lone pair, lone pair. All right, questions on primary, secondary, tertiary carbons, amines, hydrogens, or halogens or alcohols. Okay, so they all kind of follow except for the amines. Amines are backwards, so make sure you write that down. Okay, so now we want to talk and add a new functional group to our types of functional groups we have. And this is a little bit more complicated. We have before we had carbon-carbon bonds, then we had a carbon-carbon double bond and a carbon-carbon triple bond. And then we had a carbon-oxygen single bond and not this. Now we're coming up to a thing where we have a carbon-oxygen double bond, okay? And we call this the carbonyl group. It's actually the basis for a whole series of functional groups, starting with the aldehydes, ketones, and carboxylic acids. But there's a whole bunch of functional groups that use this thing. So let's talk about this carbonyl group just a little bit. The most important thing about this carbonyl group is, well, first of all, let's talk about its hybridization. There's usually going to be 2 things bonded to it over here. So what is the hybridization on carbon on this? Just look at its shape and how many bonds it has. sp2. It's sp2 because it's got 3 sigma bonds and then it has 1 pi bond. So that makes it sp2. What hybridization is the oxygen?
sp2.
sp2 because it has this electronic zone, and a sigma bond here, plus a pi bond. So it's also sp2. So we have sp2, sp2, and we have 1 sigma bond and 1 pi bond. Okay, so that's pretty cool, right? Is that a polar bond? Yes, because carbon and oxygen are two spaces apart. There's a difference in electronegativity. Oxygen is more electronegative than carbon, meaning that in our C double bond O, there's polarity toward the oxygen, right? There's more electron density on the oxygen and less electron density on that carbon. So what does that mean? If we have a carbonyl right here, this side's partially positive and this side's partially negative. Aha, it's a polar bond. It has hybridization. I think if something comes in with a negative charge, it's going to attack the carbon because it's partially positive. If something comes in with a positive charge, it's going to attack the oxygen because it's partially negative. We're seeing just by looking at its structure where things are going to react. So you can break down all of your functional groups that way. Is it a polar bond? Which side would each type of ion interact with? Okay, so in the case of this compound here, we also saw that double bonds can move around when we have resonance, okay? Double bonds can move around in resonance. And so if we drew a resonance structure for the carbonyl, we could actually break just the double bond, put those two electrons up on the oxygen, giving a full negative charge here and a full positive charge here. So these are resonance structures, okay? Which one's more stable? The one with the carbonyl intact or the one with just this carbon-oxygen single bond? The carbon-oxygen single bond's more stable or less stable? Less stable. Because, think about it, how many electrons are around carbon in this compound right here? Total is 6. You got 3 bonds, so it only has 6. So it doesn't have an octet. It's not as stable as this carbon here, which has an octet. So it has a resonance structure. The double bond moved to form a lone pair up here. So it has a resonance structure, but this one's more stable because it has a full octet around both the oxygen and the carbon. The polarity does not change. It's electronegativity. The difference in electronegativity gives us that polarity. And notice that the oxygen has the negative charge too. It's the more electronegative atom. The more electronegative atom will almost always take the electrons. Okay? So that being said, we have reactivity. We have our ability to do chemistry on here because of that resonance structure. Okay, so now let's look at some functional groups that contain that carbonyl. The first one we want to look at is the aldehyde. And the thing about the aldehyde is that you have one carbon bond, or that's not entirely true. You have at least one hydrogen bonded to your carbonyl. Okay, so if we're looking at it visually, that hydrogen on the carbonyl defines it as an aldehyde. Now, why did I hem and haw there? Well, technically, there's a compound right here with no carbons bonded to it. This is called formaldehyde. It has no carbons bonded to it, but it has hydrogens bonded to the carbonyl. So if you have a hydrogen bonded to a carbonyl, it's an aldehyde. This is the simplest one here, but most of them look something like this. Okay? And so we have that carbonyl. We usually have a carbon bond, but we always have a hydrogen bond. Okay, now if we take that hydrogen off and put 2 carbons on a carbonyl, we've changed the reactivity, we've changed the name, and we call those ketones. Okay, so the thing is that the carbon-carbon bond and the carbon-hydrogen bond, have different reactivities. So because of that reactivities, we've actually changed the type of reactions it can do, and we've changed the name and some of its properties. So we changed names. At least one hydrogen, aldehyde on a carbonyl, at least, and then with 2 carbons on a carbonyl, ketone. Okay, so are there other derivatives? Yeah, well, we started sticking oxygens on things and nitrogens on things. So let's continue on down there. So the first thing we did when we had an oxygen was we did a carbon, oxygen, hydrogen bond, and that created what functional group? Carbon, oxygen, hydrogen bond is with an alcohol. So that's an alcohol, right? But if we have a carbonyl oxygen hydrogen bond, we now have a new functional group called the carboxylic acid. Okay, it's the carboxylic acid. And this hydrogen here is, we're going to find out in our chapter 3 when we do acids and bases, is acidic. And that's why it's called a carboxylic acid. Okay, so we have our carbonyl group, we have another oxygen on here, and that gives us that functional group. So this is carbon, carbonyl, oxygen, hydrogen. That carbonyl oxygen hydrogen defines us as a carboxylic acid. Okay, now what if we take this hydrogen off? Remember when we did our going from an alcohol to an ether, we went carbon, oxygen, hydrogen for the alcohol, and then carbon, oxygen, carbon for that ether. If we change the structure again, we change the name. If we take this hydrogen off and now we have the carbonyl, oxygen, carbon, that turns it into an ester. Okay, and so we actually make esters from carboxylic acid, and we'll be doing that next semester actually, but we'll see that it has changed its chemistry. The big thing it has, the carboxylic acid is acidic. The ester no longer has an acidic hydrogen on that position. So we've changed the chemistry. We've changed the name. Okay, so then the last two I want to talk about on this page are the amide and the acid chloride. These are also carboxylic acid derivatives. Notice that if we start with the general structure for carboxylic acid up here, and we change what's bonding to this carbonyl, we have an OH here, we have an OR here, now we have a nitrogen, okay? They're all carboxylic acid derivatives, but they change chemistry, and therefore our new name when we have a nitrogen on there is amide. It's similar to amine, A-M-I-N-E, is bonded to carbons. A-M-I-D-E is bonded to a carbonyl. That D is significant. You go from an N with no carbonyl to a D with the carbonyl. And likewise, it can be primary, secondary, or tertiary, depending on how many carbons are bonded to it. Again, amides and amines are backwards. Everything else follows the rules. Okay, questions about the amide. Carbonyl, nitrogen. That is the key link there. Carbonyl, nitrogen is the amide. Okay, the last carboxylic acid derivative I want to talk about is, let's take the OH off and put on an even more nucleophilic group, one with a higher electronegativity, higher electronegativity, chlorine, right here. So we have a carbonyl with a halogen on it. Most of the time, well, technically you could make it with all the halogens, it's almost always seen with a chlorine on it. And so we have a special name for it, acid, because it looked like a carboxylic acid, but now we have chlorine on there instead of the OH, so we call it an acid chloride. But the defining structure is carbonyl bonded to the halogen, in this case, chlorine. Okay, do we see how our functional groups are changing stepwise? Our names are changing stepwise, and actually the activity is changing as well. All right, questions on these functional groups? Okay, these functional groups are going to be on the quiz on Monday. So you might want to do flashcards and do that general structure. I like the general structure here, because notice when we go from the general structure and we draw out an example right here, this group can be anything over here. The thing is, this is the functional group. That's the thing you're naming it for. So it doesn't matter what this is, a methyl or a propyl or whatever here. This is the defining feature. That's the thing you got to pay attention to in changing the name. Okay. All right. So moving on with that, we're going to go to another carboxylic acid derivative, but it doesn't look like a carboxylic acid derivative. It's called the nitrile. So the nitrile is this R, which is like there, and we have a carbon triple bonded to a nitrogen. Okay, So I'm going to convince you that this is a carboxylic acid derivative by drawing this first. R, carbonyl, nitrogen, hydrogen, and hydrogen. Okay, so what we've done is we took an amide. In fact, this is how we make it most of the time. And we take away these two hydrogens, and we take away the oxygen to turn it into water, which leaves us R, C, and then let's draw the lone pair in there. Okay. So it is a carboxylic acid derivative. We have taken water away from an amide to make what we call a nitrile. Okay, so this nitrile, it's a really cool group. C triple bond N, we still have a lone pair on that nitrogen. 8 electrons around carbon, 8 electrons around nitrogen, and therefore we have our last functional group. Okay, questions on that? Okay, so let's go ahead and do a quick summary of all of our groups here. If it only has carbon and hydrogen bonds, it's a hydrocarbon, right? And if it only has carbon-carbon single bonds, it's an alkane, A-N-E. If it has any carbon-carbon double bonds, it's an alkene, E-N-E. If it has any triple bonds between carbons, it is an alkyne, Y-N-E. Okay, so that being said, those are all of our hydrocarbons that are not aromatic. Then we had our aromatic hydrocarbons. Aromatic hydrocarbons are defined by having a ring of alternating single and double bonds. And by resonance, it's going around so fast, we really can't tell you exactly where the single or double bonds are. That's why they're aromatic. Okay. So if we look at our general formula, hydrocarbons are really simple to see. Our alkenes are really simple to see because of that double bond. Our alkynes are really easy to see because of that triple bond. The aromatic rings gets a little bit different because sometimes it's labeled pH or AR. So usually you'll see it as a substituent until next semester. If you see it as a substituent, it is just there to confuse you. It doesn't do chemistry until next semester, so don't worry about it. Okay, the next thing we had was alkyl halides. Okay, take one of those hydrogens off, replace it with any halogen, alkyl halide. And again, I like to draw, when we're first starting out, our lone pairs here, because that's telling you something about the compound. Now, all alkyl halides have polar bonds between the carbon and the halogen. So we're going to use that polarity for defining whether our molecule is polar and looking at where it's going to react. Okay, then switching it to a little bit less electronegative atom, going to oxygen here with the carbon, oxygen, hydrogen. We have the alcohol. And again, the carbon, oxygen, carbon changes it to the ether. These two are similar, but again, you have this hydrogen that can do chemistry here. There is no hydrogen there. It's going to do a little less chemistry or different chemistry. All right, questions on those classes? Because we're going to go to the next page, which has the carbonyls. Okay, so we're actually going to start with the amines right here. Any carbon nitrogen, okay? Not carbonyl nitrogen, carbon nitrogen bond, carbon nitrogen single bond is the amine. Remember, the primary, secondary, and tertiary are backwards. Write a special asterisk note there that for that and the amides are going to be backwards. Then we start with our nice little carbonyl groups. Carbonyl bonded to a hydrogen, aldehyde. Hide, there's a hide, there's an H in the name, aldehyde. So there's an H on the carbonyl. Ketone, no H, just 2 carbons. When we go to carbon, carbonyl OH, think of it as a carboxylic acid. And then the rest are carboxylic acid derivatives where we have it carbonyl OR instead of OH, carbonyl nitrogen instead of O. And then our derivative of this, where we just remove water to give us our nitrile, carbon triple bond nitrogen, nitrile. Okay? Questions on those classes of compounds? Okay, so these are the different classes of compounds. You need to recognize all of these functional groups by their generalized form for the quiz and for the rest of the semester because we'll be using them. So now I want to talk to you about, I said that they have different polarities and they have different structures and they have different chemistries. Well, I want to talk to you now about the Bobcat trace. So get your phones out and get your picture there. Everybody at home, you just have to be in the participants thing and I'll just see it there. Don't worry about having, but if you want to, you can. It's not a big deal. Okay. Okay. And again, if you don't have a smartphone, go ahead and just email me your seat name. Remember the A, B, C, D, E, F, G, H, and then the numbers on your seat. All right, there we go. All right, let's move on. So now I want to talk to you about intermolecular forces. I said when we talked about polarity of molecules, we need to pay attention to whether the molecule is polar or not, because if a polar molecule has a partially positive side and a partially negative side, it's going to want to interact with another molecule in a way which we can get a complementary action. And we call these intermolecular forces. Intramolecular with an A is a force within a molecule. We see that a lot in proteins and in carbohydrates like that. But we're talking intermolecular, meaning molecule to molecule, between two molecules, okay? So in these intermolecular interactions, we have several different types depending on the polarity of the molecule and which functional groups available to it, okay? They can get very strong or they can be very weak. And we're going to start with the weakest one that we know, and that's called the van der Waals forces. Sometimes it's called van der Waals, sometimes it's called induced dipole. Sometimes it's called London force, okay? They all mean the same thing, okay? And they're all our weakest force, okay? The next thing we have is we have what we call dipole-dipole. If you have a permanent dipole on a molecule, it's going to align with the permanent dipole on the molecule nearby. Okay, so that's our dipole-dipole interaction. That's our next interaction. So first one is van der Waals, which is induced dipole. Second one is dipole-dipole. And then hydrogen bonding. Okay, now there are things like a dipole ion interaction and hydrogen bond with an ion. We're not going to talk about those. We're just going to talk about organic molecules interacting with each other. Okay, but then we also have things that are stronger than these intermolecular forces. These are the bonds we have, which are the covalent bonds and the ionic bonds. So if we look at strength, the weakest one we have is the induced dipole, followed by dipole-dipole, followed by hydrogen bonding, followed by covalent, followed by ionic. So that makes ionic bonding the strongest bonding we have available to us in this class, okay? So strongest at the bottom, weakest to the induced dipole. Okay, so that being said, let's talk about what an induced dipole is. Okay, so let's imagine you have a happy little molecule, hexane. It has no polar bonds, right? And it has the outside of its shell is completely negative because that's where the electrons are. So it's kind of floating along and it's kind of getting close to another molecule. And they're kind of trying to repel each other, but there has to be something that keeps them close. So what happens is that instead of having that permanent dipole on that molecule, it's going to say, okay, well, I'm getting close to this molecule. I'm going to move some of my electrons to the other side, giving a slightly positive charge. And the other molecule says, hey, that's getting slightly positive. I'm going to move some of my electrons to be on that side so I can be close to that slightly positive side. So what we see is this slight, tiny change in electronegativity so that one side of the molecule becomes slightly negative and one side of the molecule becomes slightly positive. Okay, so that's just within the single molecule. But the molecule next to it is now induced to have a negative charge on one side of it and a positive charge on the other side. So now these are slightly attracted to each other, giving us our spacing between those molecules is smaller than if it was just electron repulsion by itself. Okay, so now shape is very important in this induced dipole interaction. The more of these induced dipoles you get together, the easier it is for them to line up. So the straighter or more symmetrical the molecule, the more of these forces can happen. Okay, the straighter or less branched these molecules are, the more they will interact. And therefore, there is more of that interaction. We'll see a difference in that boiling point and melting point. Okay. So if we say have something that's a whole bunch of branching, it's kind of spherical, and we have two molecules come near, the surface area between that spherical molecule and the other spherical molecule is much, much smaller than the surface area between the two linear molecules. So we have fewer induced dipole interactions, therefore less effect on the boiling point and melting point. Okay, questions on that? This is the only interaction hydrocarbons have because they have no polar bonds. Okay, so moving on to dipoles. If we do have a permanent dipole, and remember, when we look at those dipoles, we see that one side's going to be slightly positive, which is going to be the side with the less electronegative atom. And one side's going to be slightly negative, more electronegative atom. And that slightly negative side is going to be attracted to the slightly positive side of the neighboring molecule. So this is a dipole-dipole interaction. Okay, see how we have that? And because that dipole is permanent, it's stronger than the induced dipole interaction. Does that make sense? That you don't have to fake it. You already have the dipole, so you can already move forward. Okay, then what you can have, and we don't see this very much, we're going to see it in some of our mechanisms, but we have what we call a ion dipole interaction. So the ion has a full negative charge on it, and the molecules have partial positive charges. So that means you can't just take one ion and one molecule of a solvent and stick them together because not all the charges dissipate, right? But if you have 10% positive charge on a molecule, and you can squeeze 10 of them around an ion, it's balancing the charge. So that's our ion dipole interaction, okay? And in this case here, we're actually spreading the full negative charge out over 6 water molecules. So guess what? That's how we dissolve sodium chloride or sodium bromide in water. The water completely surrounds the ions and they dissolve into the solvent. So the interaction between that ion and the water is a ion dipole interaction because water has a permanent dipole. Question? Okay. So now that we're in the, we've increased from inducing a dipole to give us a weak interaction, having a permanent dipole giving us a slightly stronger interaction, let's talk about hydrogen bonding. Okay, hydrogen bonding occurs when you have a hydrogen on a nitrogen or an oxygen, okay? And it has to do with the polarity difference between the nitrogen and the hydrogen. The nitrogen and hydrogen has a polar bond, the oxygen hydrogen has a polar bond, okay? What can happen is that hydrogen is going to be the slightly positive side of that molecule. Right here, slightly positive side, and the electronegative atom is going to be the slightly negative side. If that slightly positive hydrogen can associate with a lone pair on a neighboring molecule, it will. And that's called hydrogen bonding, okay? So the hydrogen is not leaving the molecule. It's not Like an acid transfer, it's not doing that. It's staying hooked, covalently bound to its molecule, but it's attracted to the lone pair on a neighboring atom. Usually something like nitrogen or oxygen that has a lone pair available to it all the time. So this is what we call hydrogen bonding. And notice it has to do with the polarity. So if we go down one, sulfur hydrogen bond is not polar enough to hydrogen bond. So it's nitrogen hydrogen and oxygen hydrogen that are going to do our primary hydrogen bonding. Okay, that being said, we had that carboxylic acid. That carboxylic acid, that hydrogen there, will hydrogen bond, but it'll also be moved. So we have to pay attention to how we use that. All right, this kind of interaction is stronger than the dipole-dipole interaction because it doesn't just have to do one molecule. We can have another molecule here that's attracted, and then this one can be attracted to two, and this can be attracted to two. Each hydrogen can be attracted to up to 2 electronegative atoms through hydrogen bonding. So it's stronger than a dipole-dipole interaction. Okay, so van der Waals very weak, induced dipole and dipole very weak, permanent dipole stronger, hydrogen bond even stronger. Okay, so that takes us to how it changes our properties. So if induced dipole is our weakest interaction, that means that our compounds, even if they had all the same molecular weight, are going to have lower boiling points and melting points because they have less interaction between the two molecules. As we go up to higher and higher interactions between molecules, our boiling point and melting point should go up. So let's look at this. Now, these are all slightly different molecular weights, but we want to kind of say that, just kind of follow along here. If we have just the alkane here, ethane, 2 carbons, ethane, and it only has induced dipole, what we see is that it has a very low melting point and boiling point because it has very weak interaction between the molecules. And both of these boil and or melt below room temperature. In fact, it's a gas at room temperature. And so we find it we have to do different things with it. But in the case of this, we take one of those hydrogens off and put a chlorine there. It weighs more. It's going to have a slightly higher molecular weight just from that. I mean, a slightly higher more boiling point and melting point just for that. But it now has a permanent dipole. With that permanent dipole, it has dipole-dipole interactions between molecules. And our boiling point and melting point both go up. Notice they both go up. The melting point only goes up about 40 degrees, but the boiling point goes up 100 degrees. Okay, because remember, when you boil something, you have to break all molecular interactions to get it into the gas phase. In melting point, you just have to get them to start slipping past each other. So see how there's going to be a bigger effect usually on the boiling point. Okay, let's go to the aldehyde here. Aldehyde, it's actually about the same molecular weight here, but now we have a carbonyl, which also has a permanent dipole. So we have a dipole-dipole interaction, and we see about the same change in the boiling point and melting point, going from induced dipole to permanent dipole right here. So let's change that up a little bit and take it, instead of being that carbonyl compound, let's change it to an OH. Now, because we have the OH here, this has lone pairs on it, alcohol can now hydrogen bond. The carbonyl with the hydrogen on it cannot hydrogen bond. The OH can hydrogen bond. With that, we have now hydrogen bonding interaction. Now look what happens. The melting point goes up, again, not as dramatically as the boiling point. Because in the boiling point, you have to break all the hydrogen bonds, and there's more hydrogen bonds than dipole-dipole bonds because of neighboring atoms. Then when we go up to the acetic acid, it also has hydrogen bonding, but it has 2 oxygens that it can hydrogen bond to because of its structure. Therefore, the boiling point goes up even higher. And it's all hydrogen bonding. And if we take this hydrogen off and replace it with an ion such that we have an ion interaction here, we can no longer boil it. It'll melt because they'll slip past each other, but it's very hard to boil off ions. It'll decompose. And we'll see that that's the ionic interaction, which is our strongest interaction. questions on the interactions based on the functional groups and those different forces? Nothing? All right. So when we move along from that, we're going to see that we have different effects on our boiling point and our melting point. And I want to talk about boiling point specifically because that's the one where we have to break all of our intermolecular interactions. So the two forces we have here is as molecular weight increases, boiling point increases. Okay. So if they all have the same bonding, molecular weight will have the determining factor there. However, if they have stronger intermolecular forces, they're going to have higher boiling points. So if I can see my notes here, that means that things like our induced dipole things are going to have lower boiling points than our dipole-dipole interactions, which are going to have lower boiling points than things that hydrogen bond. Okay, so even if we have all the same molecular weight, we will see this trend every single time. So an example of that would be something like pentane, right here. And if we take pentane and it has a similar molecular weight to this butanol, this aldehyde, which has a similar molecular weight to this carboxylic acid, the pentane, the butanol, I'm sorry, the butanol, the aldehyde, and the carboxylic acid all have about the same molecular weight. Actually, that would only be true if I erased this one carbon. There. 1, 2. There we go. They all have about the same molecular weight, but the boiling point for pentane is 36 degrees Celsius. The boiling point for this butanol, this aldehyde, is 78 degrees Celsius. And the boiling point for this is 118 degrees Celsius. Molecular weight's not changing. The only thing that changes was the interaction. Okay, so molecular weight does change it, but if they're all the same molecular weight, look for the intermolecular interaction. All right, questions on that? Okay, so those are the two big factors on boiling points, but there's also a couple other things that we have to pay attention to. And these are secondary to our molecular weight and our type of force. But surface area plays a role. And the reason surface area plays a role is even if you have a weak interaction, the induced dipole interaction, the more of them you have, the more it will raise the melting point or boiling point. Okay. So in the case of this, we have this 3-pentanone boils at 102 degrees. Acetone boils at 56. Okay, they have slightly different molecular weights, but there's more surface for this to do induced dipole interaction, even though it still has a permanent dipole, and it can permanently dipole in more than one molecule at a time on that bigger, larger surface. So it has a higher boiling point because of surface area. The other thing that can have an effect on there is polarizability. The more polarizable your bond here is, the more it's going to have a dipole-dipole effect on a neighboring atom or multiple neighboring atoms. So in the case of here, this iodomethane actually boils at 42 degrees C, and that is a longer bond with a bigger atom. Longer bond, bigger atom means more polarizable. If it's more polarizable, it has a higher effect on that dipole-dipole. And when we go to something like this fluorine right here, which is a small atom, very polar bond, but it's very tightly held. It's a very short bond. It's less polarizable because it's a very short bond and very small atom. Therefore, it has less of an effect on the boiling point, and this is -78. Okay. Now, yes, there is a molecular weight difference, but that boiling point difference is really wide because of the polarizability. All right, questions on those total of four factors on boiling point. Molecular weight, type of interaction, surface area, polarizability. All right. Now, melting point is a little different because all we need to do is to take it from a state where they're held in a place where all they can do is vibrate. They can't slip past each other, right? So we have to break up whatever that interaction is to let them just start slipping past each other. And therefore, the stronger the intermolecular force, the more energy it takes to break that structured crystalline structure, and therefore it has a higher impact on the melting point than the weaker bonds. We saw that the melting points didn't change as dramatically until we got to the dipole, and the hydrogen bonding material. That's where the melting point really changed, is with our hydrogen bonding and our dipole ion. Okay, so we'll see that that has an effect, but there's still a problem with the idea of symmetry. Okay, the more symmetrical a molecule is, the more it's going to pack in an ordered array. The less symmetrical a molecule is, it's harder to pack it, which makes the less symmetrical molecule have a lower melting point. They don't pack as tightly, they don't have as many interactions between molecules. More symmetrical has it there. So this is backwards from boiling point on a spherical van der Waals, a spherical induced dipole and dipole versus a linear, right? Because that was just a surface area effect. And here we're talking about symmetry. Symmetry is how we pack them into a solid. Solids like to be packed in perfect little shapes. And symmetry actually gives us that higher melting point. All right, questions on boiling point or melting point and the reasons that they change. Okay, well, so that leads us to the next thing about intermolecular interactions is solubility. Okay, so we're going to actually use those molecular interactions, those intermolecular interactions, to tell us whether or not something might be soluble in that liquid. Okay, so solubility basically is you have something that you're dissolving, which is your solute, the thing that's going to be in the solvent, and then you have your solvent. So you have your solvent is the liquid, your solute is the thing you're going to dissolve in there. And so to get something to dissolve, you need to break up the intermolecular interactions of your solute with the intermolecular interactions of your solvent to get them to dissolve. So if they have the same kind of intermolecular interactions, dipole, hydrogen bonding, then guess what? This hydrogen bonding solvent can bond to a hydrogen bonding solute, and they dissolve. This induced dipole solvent and an ionic solid, nothing happens. There's no interaction that lets them do that. But you have this ionic solid and a hydrogen bonding solvent, ooh, that can probably surround one of those ions and partially solvate them. So we're looking at the interaction that lets us break up the interaction from the solute to get it to go dissolve in the solvent. So the general trend is like dissolve like. So polar compounds that have dipoles dissolve in polar compounds with dipoles. Compounds that have hydrogen bonding dissolve in compounds that have hydrogen bonding, etc. So what we have here is we have to look at the molecular structure. Number one, is it polar or not? If it's polar, it's probably going to dissolve in a polar solvent because of that dipole-dipole interaction. If it's a non-polar solvent, all of our dipoles cancel out or there are no dipoles, it's probably going to dissolve in a non-polar solvent using just the van der Waals or the induced dipole-induced dipole interaction. But then we can have things that we call weakly polar, where they have a small polar bond, So they'll probably dissolve maybe both in a non-polar solvent and maybe a little bit in a polar solvent. So we have to be careful about how we look at our dipoles. If it's strongly polar, it's probably going to dissolve in something strongly polar. If it's weakly polar, it might go into either one because it has a little bit of each of those forces. Okay? Questions on that? Nobody? All right. So when we talk about the solubility of organic molecules, we're all looking at what is going to kind of interact in which way. And so if for an example here, if we have something like pentane right here, and let's say we wanted to dissolve it, and let's say we chose something like carbon tetrachloride and water. Okay, so in here, water is a polar molecule that has hydrogen bonding available to it. Carbon tetrachloride has 4 polar bonds, but is it a polar molecule? No, because all the polar bonds cancel out. So it is a non-polar molecule. So if we have pentane, which is a non-polar molecule, it will dissolve in carbon tetrachloride because it's a non-molar molecule, but it will not dissolve in water. Interesting. So that follows the trend, like dissolves like, right? So that we have something that's non-polar is going to dissolve it, something that's not non-polar. However, this works for other things as well. Let's say we do something like acetone right here. And let's do that same thing. We want to go to the non-polar and the polar. So what is acetone? Is acetone polar or non-polar? Just look at the structure. It's got lone pairs. It's got a polar bond. So it's a polar compound, right? Just by looking at it. So in theory, it should dissolve in water because that's a polar compound, but it has this van der Waals site. It actually will also dissolve in the carbon tetrachloride. It also dissolves in carbon tetrachloride. Well, because there are permanent dipoles here, and there's a non-polar side of this molecule that will mix freely with that non-polar solvent. But this oxygen here actually can hydrogen bond with the water, giving us a strong interaction, and it also dissolves. Okay, so there's also a rule that says a functional group like water or an alcohol or something like that can typically, if it's polar, pull up to 5 carbons into a polar solvent. Above that, the non-polar side, the 6 carbon chain, dominates the 7 carbon chain, so it becomes a non-polar. But 1 OH on 5 carbons is likely to pull it into water at some. Above that, so pentanol does partially dissolve in water, hexanol does not. But then that's for each functional group. So if we put hexanol and put another OH on there, we have 2 OHs for a total of 6 carbons. So that's 3 carbons per OH. The dialcohol of hexane does dissolve in water. So 5 carbons per functional group is the general trend. Okay, questions? Okay, so I said on this acetone, we have this polar end, but we also have that little bit of methyl groups that are the non-polar side. So is that a common trend in compounds? Well, yes. We can have part of the molecule want to dissolve in water and part of the molecule not to dissolve in water. Okay, and so if the non-polar part of the water part is not attracted to water, we call that hydrophobic. Okay, so that means it's scared of water. Phobic is scared. So it's scared of water. It doesn't like to be there. And so we actually have molecules like this is a steroid right here. I think this is cholesterol. And this entire side of the molecule is non-polar. It doesn't want to dissolve in water. It has no functional groups, right? But this end of the molecule here, which I will circle in a different color, right here, this OH here wants to dissolve in water, so it's the hydrophilic. It likes water. It's the hydrophilic side of the molecule. So this molecule is used in our body. So what do? Well, it turns out we turn it into a salt, and we can use it in our bodies to have it go through our water-based system. All right, questions on hydrophilic versus hydrophobic. And this is how soaps work. You have a very long hydrophobic side and carboxylic acid or some kind of salt as the hydrophilic side. And that way, the hydrophobic side will dissolve oils, then suspend it in water and wash it away. So the water side does its function, the nonpolar side does its function, and working together, they can move molecules. Okay, so in summary, right here, our strongest interaction is ion-ion. So sodium chloride, it melts at like 3,000 degrees. Okay, so that's the strongest interaction we have. But then from there, we have covalent bonds. Covalent bonds are not as strong, okay? Like by almost an order of magnitude less strong. So, but those are the strong bonds we'll be dealing with most of the time, okay? Then we have from that dipole ion interaction. And again, it has an ion in it and the dipole, and you put a whole bunch of those dipoles around it to support that ion. The next thing we have is our hydrogen bond. Okay, so ion, covalent, ion dipole, hydrogen bonding, and that's typically the strongest interaction we see in organic chemistry most of the time, followed by the dipole-dipole, which is significantly weaker, and dispersion forces vary. That's the induced dipole, varies by what? Surface area. The more surface area you have available, the more the interaction. The less surface area you have available, the less interaction. That's why it's variable. Okay. Question on the attractive forces between molecules. So that is where we will be taking our quiz up to this slide. Okay. So the quiz on Monday will be up to this slide with the attractive forces. So all of our Lewis dot structures, our resonance structures, our functional groups, all that up to here. Okay. Then on next Wednesday, we'll start with the next one, which is IR spectroscopy. Okay, so we got what, 20 minutes or no, 25 minutes to do infrared spectroscopy. We're not going to cover the whole thing. So what I like about infrared spectroscopy is it tells you what types of bonds you have. I actually like to start with IR spectroscopy to prove to you different kind of functional groups exist because different types of bonds exist. Okay, that's why I like to have it right up here up front. Okay, so what we're doing is we're taking a part of the electromagnetic spectrum. Light, the part that we can see, is a very, very narrow window. And just outside of red is what we call infrared, or below red. Infrared, outside of red. And so it's lower energy than the light we see. Okay. But it happens to be right around the right energy to where it can start being absorbed by different kinds of chemical bonds. And when it's absorbed by different kinds of chemical bonds, that means that we don't see it in the light we just shine through. It's like when you have a blue glass window and you shine white light through it, right? And you only get blue on the other side, right? It filtered out all the other stuff, right? So you know that there's something in there that's blue. Well, in IR, we're doing the exact same thing with chemicals. We shine our IR light through and this part goes away. And you're saying, oh, great, we have a carbonyl here because it absorbed that light. That's the benefit of IR spectroscopy. It tells you which types of bonds you have, not functional groups, types of bonds. So you typically just have some kind of light source and you hit it, and most of the time we do it like multiple scans so that we can take out any noise. And what we end up with is a spectrum that tells us which wavelengths of light have been absorbed and which wavelengths of light have been transmitted through our sample. Okay, so if we look at this range of things, we can go everywhere from visible light. Actually, we can use visible light to help us do chemistry. hey, that compound's blue, that compound's red, right? Or we can go to the UV. UV can tell us something about chemical structures. It can tell us how many double bonds we have, believe it or not. We can go to the IR. IR is going to tell us what types of bonds we have between things like a carbon-carbon double bond or a carbon-carbon triple bond. But then we can actually, later on, we're going to go down way into the radio waves. And we're going to talk about NMR, nuclear magnetic resonance spectroscopy. So we're going to use all these different bands of the electromagnetic spectrum, but the one we're talking about right now is IR. And the IR is fairly short wavelength, fairly long wavelengths compared to visible light. So we're getting longer than visible light, and we're going to use that wavelength to our advantage. Okay. So a couple things we got to pay attention to is when we look at an infrared spectrum, we're going to see that the frequencies are actually given in a weird term called wave numbers, but we have to figure out where that comes from. So every bit of light has a component to it, which is the frequency. The frequency is the number of peaks per second. So if you have 1,000 peaks per second, it's 1,000 hertz. That's the peaks per second. That's the frequency. Light, of course, is much higher than that. There are much more than that. Now, when we talk about wavelength, that's the length from peak to peak. That can be very short or very long, depending on your thing. In the case of our wavelength of light that we use in infrared spectroscopy, it's 10 to the minus 4 centimeters. Okay, so a micrometer. That's the wavelength of the light. Okay, so we're starting to see it's going to be very small. Now, if we think about frequency as the number of waves, and we think about wavelength as the length of the waves, we can actually relate this to an energy by using Planck's constant. The energy of the light is equal to the Planck's constant times the frequency. Okay, so what does that mean? We can equate wavelength to energy. Wavelength equals energy. We can figure out the energy of a bond by if it's absorbed by that energy of light. Light is energy, bonds have energy. If the bond has the right energy, it's going to absorb that right energy of light. Okay, so that's what we're going to look for. And when we have this, our number of waves per centimeter, we call that our wave number. And it's called per centimeters. We call that wave number. That's what we're going to see on our x-axis of all of our IRs. Okay. So I'm not going to make you do the calculation here. I just want to show you that energy is related to frequency. Energy is related to wavelength. Energy is related to bond strength. Okay, so the number one thing we typically look at is we look for bending or stretching modes in a bond. Okay, so when we draw our structures, right, we have a carbon here, and we have a carbon here, and we draw a line between. Is that a rigid, fixed space? No, we're sharing electrons between there, and so it has some give in it, okay? So there's some frequency which this will move back and forth if it's induced. If you add a little energy to it, it'll move back and forth. Those electrons will get a little further apart, those nuclei will get a little further apart and they'll come back together, but they're gonna have some average distance. And that's our bond length, is our average distance. But it's gonna move. If you have any energy out there at all, heat, light, it's gonna move. Okay, so if we have that, there's what we call a force that you can use. Every bond strength has a spring, or it has a force that it will use. So let's say you have a very strong, very short bond. Imagine that's a very tight spring. It's still going to move, but it's going to move very fast because it's a very tight spring. Let's say you have a larger, longer bond and maybe some heavier atoms. It's going to have a more relaxed spring. So you're going to see it's going to take a lower energy to make it do. So that spring strength equates to energy. And all of our bonds have that. Okay, So, oh, we've already done that. All right. So then there's some lower energy ones that we call bending. There's bending and wagging and stretching. We see this happen in the lower energy side of the spectrum, and I'll show you where that is. But when we look at that, we're going to look primarily for that strong stretching spring vibration. But there are many other different vibrations. In fact, if you have, imagine you have methane and they're wagging in the same direction, that's going to be one energy. Wagging in different directions, that's one energy. Going in the same direction, that's one energy. Going this direction, that's another energy. So there's all these different ways that these molecules can move. So we're never going to see just one line usually, because there's all these different ways they can move. Okay, so we'll start seeing those from those stretching and bending vibrations. But the primary, the single bond vibrations are the ones we're looking for to show us what kind of bonds we have on our structure. Okay, so if you remember nothing else about IR, memorize this table. Click, you're done. All right, on for the quiz. No, let me explain why this explains everything. Okay, this chart explains to you bond energy versus bond vibration. Okay, so the first thing I want to talk about is the top line here. This line right here is our wave numbers, okay, per centimeters. Most IRs will go from 4,000 to 400 wave numbers, okay? The higher wave numbers, the higher the energy. Okay, so that means our higher energy bonds are going to be at the highest side. Okay, so why are carbon hydrogen, oxygen hydrogen, and nitrogen hydrogen the highest frequency bonds? Well, let's think about that. We have a big atom and we have a little atom. And if we had two carbon atoms, those carbons are going to be on that spring and they're going to move about the same, right? Because they're about the same mass. Now we have a carbon and a hydrogen. And that hydrogen is going to spring around like the little antenna you have, they're going to spring around all over the place right there. And so it's going to spring around very quickly. And so therefore it's going to have a very high energy that it absorbs in. So whenever we have a heavy atom and a light atom, it's going to have that high energy absorption. So in this range between 2,500 and 4,000 wave numbers, centimeters per -1, those are always going to be those light atoms, heavy atoms, springs. Okay, so we see why those are going to have that higher energy. Because think about that, hydrogen only has that s orbital. It's bound really tightly to that hybridized orbital of the carbon, and it's going to have that highest energy, highest frequency spring because it's the small atom versus the heavy atom. Now, what's the next most energy that's going to take to do that? Well, it's going to be the triple bond. The triple bond is held in very tightly as well. You have to have a very small spring, very tightly wound spring between that triple bond. So our next zone down is triple bonds. Carbon-carbon triple bond, carbon-nitrogen triple bond, between 2,500 wave numbers and 2,000 wave numbers. Do we see why it's next? Heavy atom, light atom, two heavy atoms, but bound by 3 bonds. Well, little bit less. So now that gives us our second range, and that's 2,000 to 2,500. In fact, there's almost nothing else in that range. There's only one other thing in that range, and that's the sulfur hydrogen bond. Okay, now what's next? Well, double bonds would be next, right? They're not as tightly bound as a triple bond, but they're more tightly bound than a single bond, so they're going to be next. And those show up in the 2,000 to 1,500 range. Carbon-carbon bonds, carbon-nitrogen, carbon-carbon double bonds, carbon-carbon-nitrogen, carbon-nitrogen double bonds, carbon-oxygen double bonds. So that means carbonyl compounds, all those carbonyl compounds are going to show up here. Ooh, we're starting to see functional groups. All right. And I have 13 minutes. Then down below 1,500, we have these single bonds. Carbon-carbon single bonds, carbon-oxygen single bonds, oxygen-oxygen single bonds, halogens, all those single bonds here. These are sometimes hard to tell because this is also where the wagging and the stretch, all these other modes come in. They're the lower energy modes. They all show up here. So we usually help identify where our different bond types are, and maybe even our functional groups, by looking at these top three ranges first, and then verifying that we have these other things in there. Okay, so the next thing I want to talk about is intensity. Okay, the more polarizable the bond is, the more intense it will be. Which means if you have an acetylene, triple bond, it's going to be a very weak signal because the carbon-carbon triple bond is not polar. It has that high energy, but it might not be very strong. However, what about the carbonyl? Strong dipole. It's one of our strongest bonds we'll see is the carbon-oxygen double bond. So polarizability increases the intensity we see in our signal. The energy of the bond tells us which zone we're going to be in, which region we're going to be in. All right, questions on that? Okay. So again, figure out which types of functional groups would fall into which of these bands. It can be more than one. Like nitrile will be only here. But if you have a carbonyl and maybe something else, an oxygen over here, you have a carboxylic acid, you're going to have a peak here and a peak here. So you're looking for types of bonds in the different regions, not functional groups. And do those functional groups have each of those types of functional bonds? Functional group has multiple different kinds of bonds. You have to look for different types of bonds. Okay. Next thing we're going to do is common frequencies. Now, if you're a numbers person, you like to memorize things, this is where to go. But again, we can look for these kind of information just by studying that other chart there. We have our carbon-nitrogen triple bond, our carbon-carbon double bond, a triple bond between that 2000 and 2500, and they can be medium to weak. Notice that the nitrile is medium, but the triple bond, the acetylene, is weak to medium. There's a difference in electronegativity between the carbon and the nitrogen. Therefore, it has a permanent dipole. Therefore, it's automatically stronger than a carbon-carbon triple bond because it has more polar, it's more polar. Okay, so we're going to see that. Then if we look at the carbon-carbon double bond, we can actually see that between 1600 and 1700, and it's medium. The more unsymmetrical it is, the stronger it gets. So if you have it just hanging off one side, the more unsymmetrical, the stronger that gets. The more symmetrical, the weaker it gets. The carbon-nitrogen double bond shows up in that same range and is medium because it has that permanent dipole. But again, they're right next to each other. It's not very strong. The difference between those is not as strong as the carbon-oxygen. And that's why the carbon-oxygen, which is down below, is always strong. So if we look here, the carbon-nitrogen double bond versus the carbon-oxygen double bond, this is strong and this is medium. There's a bigger difference in electronegativity between the carbon and the oxygen than the carbon and the nitrogen. That's why it's stronger. That's why we're going to see it more intense. Then we have our single bonds down here between heavy atoms. Okay, our single bonds between heavy atoms, which, you know, are anything but hydrogen, are going to be lower than that 1500. And they can be strong or medium or weak depending on the difference in electronegativity. Notice the carbon oxygen is stronger than the carbon nitrogen. Difference in electronegativity. Okay, and then we move on to our light atoms with our heavy atoms, our hydrogens bonded to other things. Okay, that's where we get the high frequency stuff, up above 2500. In fact, most of them are right around 3000 or above, except for the OH on a carboxylic acid. It's the one that dribbles down to the 2500. Okay, and we'll see that it has a distinct feature. But all the rest of them are pretty close to above 3000. Right here. And again, they tend to have strong peaks and they have unique broad peaks. Now, I say they have broad peaks. We just found out that alcohols and carboxylic acids and amines have hydrogen bonding hydrogens. Hydrogen bonding can be one, two, or many. So you have a whole bunch of different types of hydrogen bonds, and that broadens the peak out. Those peaks are broad because of hydrogen bonding. Okay? They're intense because of the difference in electronegativity. They're high in frequency because it's heavy atom, light atom, but they're broad because of hydrogen bonding. All right, so let's look at some common ways we would look at a IR spectrum. Okay, so what we're going to do is we're going to start typically up at 4,000 and work our way down and start looking at the different zones and figure out what kind of bonds we have available to us. Let's say we don't know what we have, we just have a spectrum here. And so the first thing we want to do is look at, let's look at everything above 3,000. Okay, we have nothing above 3,000, which means we have no OH, no NH, no, nothing like that. Okay, so we have none of those right there. We don't have any really strong carbon hydrogen bonds either. But now we look at the 2,500 right here, that's where we go. The 2,500 to this is where all the carbon hydrogens, oxygen hydrogens, and nitrogen hydrogens are. Now, we have a peak just below 3,000. Just below 3,000 is what we call an sp3 carbon attached to hydrogen. Write that down. Below 3,000, we have sp3 hybridized carbons bonded to hydrogen. Okay, so that means that we have this right here is all hydrogens bonded to sp3 carbons. Luckily, if we look at our structure, I think we can believe that, right? There seems to be no double bonds, so we only have sp3 hybridized carbons, and therefore that seems to be true. Then we have nothing in our next zone, our 2,500 to 2,000. So we have no triple bonds, no carbon-carbon triple bonds, no carbon-nitrogen triple bonds. And then we go down to 1,500, which is about right here. We have no double bonds, no carbon-carbon double bonds, no carbon-nitrogen double bonds, no carbon-oxygen double bonds. Then we go below that. Okay, this is where we're going to get carbon-carbon bonds and bending modes and stuff like that. So what we're seeing here is that this is what we call the fingerprint region. We call it that because there can be lots of different bonds there, lots of different lines there, from bendings to twistings to waggings. And if you have a computer, it'll computer match that fingerprint region from different compounds, and you can actually get very high levels of confidence that you have exactly pentane versus exactly hectane. Even though it's two carbons difference, they're going to have a difference in that fingerprint region. But for us, what we're looking for is the three top zones tells us the different types of bonds we have. The fingerprint region proves that we have our carbon-carbon bond or our carbon-oxygen bonds or our carbon-chlorine. Questions on alkanes? So if we change this alkane and go from sp3 hybridized carbons to having an alkene, which has sp2 hybridized carbons, we should see a difference. Okay, so again, what I usually do is I draw that line right at 3,000, right here. Notice we have peaks below 3,000, which are what? sp3 hybridized carbons attached to hydrogen. Okay, but we have a peak above that now. We didn't have that in the previous spectrum. We have it in this one, which means we have sp2 hybridized carbon attached to a nitrogen hydrogen. Notice it's higher in energy. Okay, I'll give you a quick idea why. In the sp3, we have 25% S character, 25% S character. That's a small one that's round in the middle, right? So it is only 25% S. sp2 is 33% S character. It's held in a little tighter, higher frequency. What's going to happen when we go to acetylene, when we have an SP? It's going to go up again because we have 50% S character. So look at it that way if you want to figure out where sp3 is lower in energy than sp2, which is going to be lower in energy than sp. Okay, so we've identified our sp2 and our sp3s here. And then notice we have this peak above 1500, between 2000 and 1500. That's where we're going to see our double bonds, but it's weak. Well, okay, I'm sorry, I skipped something. Here's our 2500 to 2000 here. Nothing there. No triple bond. Just double checking. Now we have this weak right here, okay? And I said that carbon-carbon bond is not polar. And it goes from weak to medium depending on how unsymmetrical it is, okay? Here we have a non-polar bond. Here we have hydrogens that are also fairly non-polar bonds. So it's going to give us a weak signal. If we put something like a chlorine on it right over here, it might get stronger. Okay, and then that takes us into the 2000 to the 1500 range. So that's the only thing there. So that's our double bond as well. So that's our, yeah, that's our double bond. So we have those two weak things that we have in that range. This one's stronger because we have an unsymmetrical thing. This is weak. Again, it's a carbon-carbon bond. And then everything else is in the fingerprint region. And so we have different peaks here than we had before. Okay, make sense? So that means when we look at the next one, the aromatic ring changes again, okay? So in the case of the aromatic ring, we're gonna draw that line right at 3000 again. Oops, that didn't do a very good job. And the hydrogen on that benzene ring is on a sp2 hybridized carbon. So it's going to show up above 3000, but we have sp3 hybridized carbon, so it shows below 3000. But remember, in an aromatic ring, that's not always a single bond and a double bond. They're moving around. So we have what we call combination bands. Those are mixing of the different carbon-carbon double bonds. And then we have no other functional group below 1500. This is 1500. This is 2000. This is only carbon-carbon double bonds. And then we have this carbon-carbon single bond. All right, we'll pick up here on Monday. Again, quiz on Monday is only up there to molecular reactions. Quiz on Wednesday will contain IR. All right, I'm going to go ahead and stop sharing and stop recording.